Hello everyone. So today we'll be covering about the loss function and the regression loss. Okay, so first of all, what is loss function? So before going, we'll see that imagine you are giving a student you are a student and you are giving a test. The score tells you that how well you did. Now flip that. A loss function is something like a inverted score for your neural network. A loss of 0 means that the model is perfectly predicting. A high loss means that the model is getting things badly. Mathematically, a loss function takes the model predicted value and the true label and give you back a single value, always non-negative, that will tell you that how wrongly your model is. So here are some of the key insight about it, that the loss function is the only signal of the neural network that gets during the training part. If you pick a wrong loss function for your task, your model will learn it completely wrong direction. Okay, so what makes a good loss function? It should be differentiable, because back propagation need to compute the gradients. It need to be non-negative. It need to be task appropriate, like regression, classification, and generally all other needed different other loss function. And if needed to be on the sensitive or to the errors, there's a big mistake you make while having a big loss function. Okay, so now let's talk about the regression loss function, starting with the MSE, mean squared error. It is probably the most commonly used loss function. The formula is simple. You take the difference between your prediction and the true values, square it, and average it across all the samples. Now, why squaring? Because squaring does two things. It makes all the error positive. It punishes a large error much more heavier. An error of cost of 2 4 times more than an error of 1. This means that the model get a very strong signal when it makes a big mistake. MSE is smooth, easy to differentiate everywhere, and the gradient is proportional to the error. So large error gets larger correction automatically. Now here's a problem also, that MSE is extremely sensitive to outliers. If even a few points have extreme values, MSE will force your model down to overcorrect for those outliers and underfit the rest of your data. Okay, so next up we have the mean absolute error, MAE. Instead of just squaring, what you do is you take the absolute value of this mean error for everything, panelize equally regardless of the size. An error of 10 cost exactly 10 times an error of 1, not 100 times like in MSE. Okay, so this make MSE more robust to outliers. Now there's a trade-off. The gradient of MAE is always constant, either +1 or -1. So the model get no information about how large your going script to be. Okay. So now moving forward towards next, what brings up the best of both of them is the Herbert loss. Herbert loss is a hybrid form. For small error below a threshold called as delta, it behave like MSE, giving you the information about the propagational gradient. For large error above delta, it switches to behavior like a MAE. So outliner don't explode your losses. Delta is a hyperparameter that you tune yourself. Herbert is smooth and differentiable everywhere, robust to the outliners, but still informative near zero. This is the standard choice for the robust regression task. Okay, now moving forward towards the section 2 about the classification loss function. So it is the binary cross entropy, also called as log loss. This is used when you have a binary classification problem, yes or no, cat or not cat. Your output goes through a sigmoid activation that will give you a probability between 0 and 1. The formula penalizes the model based on the how confidence and how much wrong it was. Here's a beautiful part about it. When the true label is 1 and your model predict close to 0, the loss shorted up to infinity. But when your model correctly predict close to 1, the loss dropped to 0. Okay, now you might ask that why not just use the MSE for classification? Great question. But when your model is confidently wrong and you use MSE with a sigmoid output, the gradient become extremely flat. The network barely learn anything, but the binary cross entropy, the gradient are steep, and exactly what the causes us that where the model exactly goes wrong. Okay, we have a categorical cross entropy also for the multiple class. When you have more than two classes, say cat, dog, bird, you have categorical cross entropy. Your label are one hot encoding and the output goes to the softmax layer. Now we have a quick example for this. Take true class is cat and the model gives a probability of cat as 0.7. The loss is negative log of 0.7, that is about 0.36. If the model give cat only 0.1 probability, the loss jumps to 2.3, much higher penalty for being the wrong. So this is why you have to always pair softmax output with the CCE. Okay. CC is basically categorical cross entropy. Okay, now we have one more sparse categorical cross entropy. So this is mathematically identical to CC, but instead of one hot encoded label, you just passes it integer classes indices. Okay, so instead of writing 0 1 0 0, you just write 1. This is much more memory efficient and uses in NLP vocabulary task. Okay, we have hinge loss also. This one come from the word of support vector machine, label +1 -1. We have covered this complete hinge loss in the support vector machine part. Okay, moving forward towards the KL divergence. So basically what happen is that it measures that how much difference is there in the probability distribution of one from the another. It is always non-negative and equal to 0 when the two distributions are identical. One more important thing is that KL divergence is asymmetrical. The divergence from P to Q is not same as Q to P. Okay, so now what it does is that when the true labels are one hot CCE and the KL divergence, they differentiate only just by a constant. Okay, we can also see that KL divergence show up mostly prominently in the variational autoencoder. We'll be discussing a project over variational autoencoder, so there we'll discuss it about it. Okay, now moving towards the section 3 is choosing the right loss function. Okay, so here's the complete game about it. We have some of the golden rules that how you can choose, and these just burn them into your memory. Rule number 1, always pair the loss function with the right output of the activation function. CCE needs softmax, BCE needs sigmoid, MSE needs a linear output. Mixing all of them up can be a common mistake for the beginners. Rule 2, for regression, always check for outliner first. If they are present, go with the harbor. If your data is clean, then MSE is fine. Rule 3, never use MSE for classification. Always use cross entropy. The gradient behavior is completely different. MSE have a flat gradient when your model is confidently wrong, while cross entropy have steep gradient. BC train classification many a times faster. Rule 4 is, for imbalanced classes, look into focal loss, which is a weighted variance of BC, and downweight easy samples and force the model to focus on the hard ones. Now, one of the most important thing, that the big picture. Why does this all matter? Let's come to the fundamental insight from where we have started. The loss function is the only training signal that tells your neural network what you have to receive. Every weight update, every gradient, every bit of learning, it allows us only via the loss function. MSE squared error, powerful for linear regression but dangerous for the outliner. MA is linear and robust but losses gradient information. Haber combine both intelligently. Cross entropy aggressively penalize the confident wrong prediction. That's why classification training is so much faster than the normal MSE. Okay, so now let's these are about the hinge loss also. So now let's wrap up about it. So you know everything about the loss function in the neural network, from MSE to the MA, from the binary and the categorical cross entropy to all towards the hinge loss and the KL divergence. Maybe this will be helping you out. Thank you. We'll be covering more topics relatively in coming videos. Thank you.